Hello, welcome to my cozy office as we learn about the House of Quality. Yes, welcome to my home. In today's home, we will be studying that quality. Is my home comfy? Of course it is. So it's been a while since we've had some lecture videos. I didn't want to post lecture videos while we were actively working on Project 1. So you will see that we're now entering into Project 2, and it's time to start talking about some processes again. Now, some of the important things that we really need to talk about before getting started in Project 2 is I'm going to introduce Project 2 to you a little bit later this week. I'll give you an idea of what it is in the next lecture, which I will post today. But really I'm more focused on figuring out groups, getting SolidWorks stuff. And that's what we're going to spend today in class doing. But just as a note for all of you who care about getting good grades in this class and care about learning the actual material, everything that we've done so far in this class kind of culminates in Project 2. We had to do a lot of things in Project 1. Okay, so Project 1, we worked on things like professionalism. Most of Project 1 was about professionalism. How do you as an engineer professionally make decisions and then professionally communicate them? Okay, and communication involves two steps. One is, what did you decide? And step two is, why did you decide it? Okay, that was all Project 1 stuff. Now, making decisions was part of your design process overall. Every one of you had to make decisions what your park was going to look like, how it was going to be laid out. Communicating them, what you decided to do was your AutoCAD. And that's really how I graded your AutoCAD stuff. Did you make decisions and then communicate effectively what decisions you made? Okay, involves a lot of critical thinking, a lot of foresight, a lot of really putting yourself into the situation, solving the problem. And that's really what engineering is. Now, why you decided to do those things, this was your presentation. This ended up being very similar to a sales pitch. And that's the way it should have been. And that's okay. Some of you just went straight sales pitch. Some of you went more for a more technical discussion, both of which are okay. What I was mostly looking for is, why did you make the decisions that you made? And I think pretty much every group did an exceptional job of explaining this. Some groups did a better job than others, but I still was very impressed with the quality of what everybody was explaining for their decision-making process. I'm excited to see what all of you had done for your Project 1, and now going into Project 2, I'm really excited to see what you're going to do again. Because this is now an extension of, you've shown me you can do this. And this is foundational to engineering. But now Project 2, we work on the gritty details, okay? So one of the big features of Project 2 is that your teams are going to be slightly larger, okay? And one of my purposes for making your team slightly larger is because you do have a lot more to do this round. The CAD work itself, I mean, it's tedious, and there's little display things that have to be done, but there's a lot of things that have to be done in this type of project. Now, the format for how I'm going to give you this project is very similar to how I gave you the last one. I'm going to step you through exactly how I'm going to design it. You're going to watch me design it. You're going to be able to use those videos in assistance to how you work. I've noted some students have been taking notes during these videos, just so that if they run into an issue while they're working on their project, they can go back and reference certain positions in the videos and be able to find them again. That helps you, great. But as we move towards project 2, everything that we did here for professionalism applies again. Because this is an engineering project, you have to make decisions. You have to communicate them. Both of those are foundational needs in engineering. So we haven't lost this element. But it's only one piece of it. Your groups are going to be larger, which means now you have a team dynamic. And the team dynamic is going to be one of the most important pieces of Project 2. Okay? One of the things we're going to be doing in class this week, if you're not able to attend class this week, please let me know in advance. I can throw you in a group. Whenever you have a team, you have to have formal relationships between your team members. Okay? Which means we're going to be dealing with contracts. Everybody's going to have to sign a contract. Yes, it's added work, but you're going to have to, I'll give you a baseline contract to work off of. You're going to have to write the contract. Okay? And then everybody's going to have to sign it. Everybody's going to have to agree on it. If you absolutely refuse to agree with any of your contracts, I mean, I don't even know why you're going into engineering at that point. but it's something where you gotta work with people, and the contract exists to protect individuals. We'll talk a little bit more about that when I show it up in class this week. So we'll be talking about contracts. 1. Second, we're going to have 1 team health assessment. We talked about this in a lecture at one point. We're going to be doing this in class later on this semester. It'll be in the middle of April. Okay? I need to know how your teams are doing, and you have to rate each other. Everybody has to provide feedback. It's got to be a process. Okay? And ultimately, how your team performs, the best teams will produce the best products. I already know that. You can have stellar individuals on a team, but if you aren't working together, your project will be terrible. I just know that right now. There's a huge difference. One of the reasons why I like the sport football, because you can have standout athletes in the sport of football who do not themselves cause their team to win. You can have Tom Brady, who is, I don't like the man personally, and nor do I root against every team he ever plays on. But you can have a guy like Tom Brady who is just an outstanding quarterback. And why doesn't he win the Super Bowl every year? Well, it's because the team has to work too. There's 21 other people out on the field who... Oh, and more if you count special teams and backups and all that, but there's a bunch of other people that rely on each other in order to win the game. You can't just have one person win the game. You have a standout person on your team, that's great. You will have certain aspects of your design that are great, but if your whole team does not work together, your project will fail. Okay? And so the teamwork aspect of Project 2 it becomes much more critical. Okay, as a part of the team dynamic, you're going to have to assign a project manager. Somebody has to manage this project. And it's a requirement. You have to have it. Everybody has to have titles when you establish the contracts. So this is going to be a critical aspect. In addition to this, though, we're going to have a few other pieces that we're gonna really play around with in this. First of all, I'm going to expect you to talk a lot more about the actual design decisions that were made. Okay, so I should messing up my design decisions. Okay, one of those aspects is Pew matrices. We haven't talked about that yet. One of those aspects is the SWOT analysis. Okay, we have talked about this. You may need to go back and refresh yourself on your memory. This will be one of the expectations in Project 2. We're going to have to talk about what we're going to talk about today, which is the house of quality. I will give you a template for that a little bit later on in the semester. I have to get it. But we're going to be talking about design decisions not just as a presentation form now, but actual as tangible data. Okay? And all of this is going towards what is the final product for Project 2, which again is going to be twofold. Well, actually kind of threefold, but never mind. Your deliverables for this project are going to be a proposal, which is going to be a written document. I will give you the proposal outline when I provide you with the Project 1 details later this week. And then you will also be giving a poster presentation. Okay. So Project 2 is just a little bit, it's a lot more of the actual engineering stuff. It's everything we've been talking about this semester put into the project. Now, everybody did a pretty good job on Project 1, but here the expectations for Project 2 are that I know your Project 1 is done. We can do this. We're going to do this. Let's put everything we learned from Project 1 into Project 2 now. Okay, so that's where we stand. If you have any questions, we'll talk about this a little bit more in class this week, so bring your questions to class. On the other side of this, let's talk about the house of quality. So I put house of quality under your engineering design decisions because really a lot of these tools are meant to assist you when you make decisions in your engineering design process. So a house of quality, I believe it was a concept that was originally developed in the 1970s. But the idea was we need a method that identifies the way that a design works, compares it objectively to something else, and produces design data for, first of all, how we can make it better, but second of all, whether or not we should pursue this design. Now, chapter 6 in your textbook is, the entire chapter is all about house of quality. It's a long chapter. It's a good chapter to read, but what I'm going to end up doing is give you this lecture, and this lecture will kind of cover everything that isn't the house of quality. I'll talk briefly about what the house of quality is, but I mean, there's a lot of sections that are very specific to pieces of the house of quality, and that will be your reading assignment that I give you. I assume I haven't given you that one already. I have to go back and check, because I may need to modify it. We're going to have to change up a little bit our lectures just because I gave everybody an extra week on their Project 1. We're behind a week on where we're supposed to be. So it is what it is. Less time for SolidWorks, but I was happy with Project 1 results. Okay, so when it comes to house of quality, what is it? Well, house of quality looks like this. A full form house of quality takes this shape, and it generally has the shape of a house. You'll notice in your textbook, figure 6.5 gives an example of the house of quality being used. House of quality is a feature that it's pretty universal. This is an international method that people have done to evaluate their own decisions and to determine whether or not their decisions are valid. So this isn't something that's unique to the US. It's really used everywhere. But the house of quality is generally built, got to make sure that Yeah, like this. Here you have your functional requirements. Up here, you have, well, on this row right here, which goes right underneath the triangle, this is all of your form, which are the ways that you accomplish the functions. Up here you have your relationships between forms. Over here you have your existing technology. Down here you have your, what is it? I believe the weights are down here. Oh no, sorry, this isn't the weights. The weights are actually right here. And then down here, these are scores. Okay, so the whole purpose of what we're doing with this is we take, you'll notice your functional requirements. That's a process that you should have accomplished in the very first step of the problem framing. It's coming up with what kind of functional requirements are you having for your device. Your form steps into the second step of your design process, which is your ideation. How do you solve each of the individual functional requirements? What are the exact mechanisms needed to solve that? Over here, you rate your existing technology. Up here, you rate the relationship between your different forms to see how interdependent they are. Okay, if the speed of your vehicle, your vehicle needs to go quickly. If the speed of your vehicle is dependent on not just, the size of the engine, but also on the size of your tires, it means that when you go to pick a tire for your design, you have to keep speed in mind as well as how durable it is, how well it handles conditions, how well it does off-road. There's many aspects that you now have to consider when it comes to a wheel, and there's that interdependency actually makes the design weaker. If you can choose a tire that is completely independent of the amount of speed that the vehicle has, it's a best case scenario. Okay, so the whole purpose of why we create this is it gives you a really good in-depth evaluation for your product. Usually the house of quality, if we write out our 4 steps, you get your problem framing, you have your ideation, you get your realization, which is where you build a prototype, and you have your analysis. Usually the house of quality goes right in here. After you have picked your idea of what you want to pursue, you then do this, and the end result of this should be a more optimized solution. Okay? This isn't going to help you make design decisions such like, should this have wheels or should it have treads? That's not what this is used for. Now you could use this to make that decision, but the process of building one of these is pretty intensive, so I wouldn't use it for that. What I would more look like is use this data to give you information on how can you make your design better, okay? So let's go through a very, very simple example. Book goes through examples. You can find videos online. I'm probably going to post a video just as an addition to this about somebody using the house of quality, because there's tons of examples online. Not everybody does it the same way either. So, I mean, pick and choose. We're going to try to stay pretty close to this book just because this is the resource I'm teaching you. But do be aware that some people will not just put functional requirements, but will also put constraints on this. And I tend to do that myself if this is just me in a higher level class. But I'm trying to teach the book, so keep it there. All right, so let's do an example. Now let's say I am designing an air conditioning system, okay? So I'm trying to come up with a house of quality for an air conditioner. Over here, I'm going to start with step 1, which is my functional requirements. What all does an air conditioner do? Now, according to the book, it usually has you compare what is it that, you have classifications of functional requirements, like cools air, and it is these steps. Replaces oxygen, these steps. And you can break functional requirements into pieces. I'm going to go ahead and take that approach now, just so that you can see an idea of how this is done. So, with functional requirements, okay, yes, cool air. That's going to be a big feature of this. As a part of cooling the air, processes that are involved are remove heat from space. So like you want the heat that's in the building to go out of the building. Okay? You then want to transfer heat to environment. And there's two processes there, because you have to take that heat and you have to move it somewhere. It has to come from somewhere, has to go to somewhere. You don't just accumulate heat, or else you're building lava. Yeah. Okay, and those are going to be my two steps that are involved in the functional requirement, which is cool the air. Okay, second functional requirement is going to be it has to circulate air. Okay, so by doing that, it's going to have to intake space air, because it's going to have to, at some point, suck some air in. It's going to have to output space air. It's got to go from somewhere. It's got to go to somewhere. And it's got to be something where it encourages airflow. So creates airflow. Okay, and my last functional requirement that I'm going to give this one is it has to refresh the air. And what does that mean? Well, it means that I breathe out a lot of carbon dioxide because I murder the environment with my body. No, I'm kidding. Actually, carbon dioxide is good for plants. So I'm making a tree healthy somewhere. Look at all that health. You produce a lot of carbon dioxide. You need to bring in oxygen. You need to bring in, when we breathe out, it's not just carbon dioxide. There's also water content. There's a lot of different things. You want to be able to bring in clean air, so to speak, from the environment that gives you more oxygen in your area. So I'm just going to have that be its own step. Bring in new oxygen. And there's a bunch of other things that air conditioning systems do, like they reduce the humidity, air-water concentration. You can have air conditioning systems that also heat the air. You can have air conditioning systems that filter the air. In fact, every one of them does. So we could make this list a lot longer and then talk about the individual steps that are involved in doing each one of those functional requirements. But in general, this is a very, very simple air conditioning system. Okay. Now, the second step of what you're supposed to do, I guess according to the book, I missed step 1, which is who your consumer base is. You're supposed to identify who you are consuming for and what kind of, yeah. So I guess this is step 2. Step 1 is consumers. Your book lists this as a who. What kind of people use air conditioning systems? Well, you're going to have you could list out a number of people who are associated with it. I mean, here you've got regular users. And here you got maintenance individuals. Then you can talk about manufacturing individuals too, but I'm just going to care about these two groups as of right now. Okay. So step 3, so this here is supposed to be step 1, this here is supposed to be step 2. Step 3 is applying weights. And when we talk about weights, it's how important is each one of these to the individual. And that is something that becomes a little bit more oh, shoot. Yeah, hold on, before we get into this. Each one of these has an associated measure of quality. And that actually does go into step 2. Each one of these has an associated measure of quality. So, okay, so here I'm just listing out measures of quality. Associated with each of these functional requirements. I'm also going to list out a few other ones. Cost. You can talk about ease of maintenance. Handwriting sucks. But we list out a bunch of different measures of quality. And this is where they go. We've kind of arranged them into functional requirement measures of quality, and then other ones that don't have anything to do with functional requirements. Although we could probably add a functional requirement like has to be able to be maintained, has to be able to be purchased. In fact, I probably should do that. So, purchasable, and then maintainable. There we go. So now I've got all of my measures of quality. I have all my functional requirements. I have them linked together so that each one of them is related to an aspect of the functional requirements. This is a good way of measuring how well it does the solution process. All of these are constraints that have to be provided for by the drawing. That's how I usually like to do it. All of these are measures of quality that identify how well it does it. Okay, and then we have our users and maintenance group over here, and we'll just slide that over on the end. Okay, so 1, consumers. 2, functional requirements, measures of quality and constraints. 3, we're gonna put together the weights. So how important is it to a user, the amount of heat removed? Well, that's probably a 10. In fact, we don't even care about how fast it goes. We care about most, like how much heat does this produce? Usually your weight, what you do is you scale it on a scale of 1 to 10. What is the most important? Some weight categories will actually go ahead and say, just rank this 1 through 10. Some people will just say arbitrary values. This is 24 times more valuable than this, or this is 38 times more valuable than this. So we'll pick our least important one, we'll put it at 1. We'll pick our most important one and see it as like a scale value of that one. Yeah, you can do that. Generally, you try to keep your weights pretty low, because otherwise if you start getting into, really as soon as you get into 20, 30, 40, 50, your numbers start to get extremely skewed towards exactly one measure of quality. So I would say probably you shouldn't have a number really over 20. I know the book has a number that goes into 24. I'm looking at it right now, but 20 is usually the maximum here. I'm going to go ahead and put this as, you know what, I'm going to go ahead and say that this is a 20. I don't care how you do it. I don't care about the environment. dang it, just cool my house. Okay, speed of heat removal, that is important for how much heat is transferred to the environment. It is important, so I'm going to go ahead and put this as a 12. Refresh rate, I mean, you'll start choking up, but most people don't consider that as important. Percent of homes serviced, yeah, that is important. Again, I'm going to leave that as an 8. Oxygenation level, I mean, those are up to standards, quite frankly. People don't want to be suffocating, but you do want to have sufficient oxygen. But at the same time, like, oxygenation is probably isn't high on somebody's list of like, I'm looking for a high oxygen content. Cost is usually pretty high. I'm going to go ahead and throw this as a 15. Ease of maintenance, I'm going to drop this to a 2. Because, quite frankly, we throw this to a maintenance guy and it's like, you fix it, it's not my problem. Now, on the other side of this, maintenance is a little bit different. Maintenance doesn't care about how much heat is removed, and quite frankly, doesn't really care about how fast it happens. The maintenance guy does care about the refresh rate because that's part of the design process. So you are going to be looking at, he's going to be looking at obstructions, he's going to be looking at making sure that flow rates are necessary, and really be looking at the fact that a lot of this has to service the whole house. Your oxygenation level is going to be important to the maintenance and repair guy because they're wanting to make sure that this unit is sufficient. If you maintain a product and all the people die in your house because you didn't have sufficient oxygenation level, that's important. Cost is a 1. They don't care about how much your unit costs. Maintainability, yeah, there's your 20. So here, if we're designing for 2 different groups of people, those are the weights that we're going to have. This is just going to be a relativistic number. Now here in the middle, well, before we get there, we're going to talk about this piece up here. Okay, now that piece up there is your form. Okay, it's the actual physical construction of the unit. Now I'm going to simplify this form substantially just because I'm trying to speed up this video a little bit, but items that you would have for your form is like outside coils. They're the actual coils of air that are on the outside that exchange gas with the environment. Okay, then you have your, you're gonna have some refrigerant flow connection tubes that go between the air conditioning unit outside and whatever the air conditioning unit inside is. So you have your connections. You have your power supply. You're going to have an internal unit, and the whole purpose of that is it's just installed somewhere. You're going to have your vents and your registers, and then you're going to have your intake somewhere else. Okay. Now there are more components to this. I'm just going quickly. Now what we're going to do down here is we're going to rate using 3 different rating styles how critical each of these forms are to accomplishing these measures of quality and these functional requirements. Okay, so the outside coils, are they important for removing heat from the space and ultimately talking about the amount of heat removed? No. So this one just, it gets a no mark at all. It comes in as an empty space. Okay. I mean, they may have, I guess, a little bit of, but yeah, no, I'm just going to leave that as an empty. Now, the speed of the heat removal is highly dependent on the outside coils because the outside coils are ultimately what's transferring the heat to the environment. So here, for that one, I'm going to go ahead and what the book uses is they do a circle with a dot in it. So we'll go ahead and follow that same convention. I'm trying to keep my lines straight. See how good I am at drawing matrices. Okay, refresh rate actually has nothing to do with refresh rate. So again, that's nothing. Percent of the home service, oxygenation level, cost. There is a very small associated with how many coils there are with the cost, and how easy it is to maintain. So I'm going to go ahead and say a minimal relationship. This is a maximum relationship. So if I go over here and say max relationship, meaning very, very impactful. This has a value of 9. Your circle is a moderate relationship. It has a value of 3. And then a triangle is minimal. It has a value of 1. Okay, we'll talk about what those mean later. Here, as far as cost goes, I wouldn't say it's a huge part of the cost, so I'm going to go ahead and draw this triangle. Ease of maintenance. The coils are a substantial area where there is maintenance required, so I'll go ahead and put that as a moderate. And we'll keep going through all of these. The connections themselves, yes, it does actually influence a small amount. The amount of heat removed has a little bit more importance on the rate of their heat removal, so has a moderate relationship here, but has a minimal relationship between your connections and the amount of heat removed from the space. No impact on the refresh rate, percent of home service, oxygenation. Really doesn't even have an impact on the cost. Your connections kind of, they're not all that. And ease of maintenance actually has a very, very powerful, because how you connect things are really critical for how things are maintained. Power that's being brought into the system, it is going to have a relationship on these two significantly. The more power you have, the better the fan you can get. It's not going to really impact this or oxygenation level. It is going to impact the cost. More powerful units mean more units can handle it, but it's going to have no impact on ease of maintenance. Your internal unit that goes inside of your house, this is where space air is mixed with outside air. It's got some fans. You're going to have air intake from the outside. This is going to have the most critical aspect of how it actually removes heat from the space. So you'll be cycling that air, pulling it out. And it does have a small relationship on the speed of the heat removal, just because a lot of that comes from the outside coils themselves. Now this has probably, it's a moderate relationship between the refresh rate. This doesn't impact the percent of home serviced, but it's probably the unit that impacts the oxygenation level the most. Here it does impact cost. And here, this one is probably where you're going to spend most of your time with maintenance. Okay, vents don't really impact these two. It has moderate relationship here, has a big relationship here. Doesn't really impact anything else. Although it has a small relationship in cost, just because the more vents you have, the more it's going to cost. Similarly with intake that comes from the house itself, you're going to have a small relationship to the amount of heat that's removed. Depending on where you put that intake, you may or may not get very much heat you're actually taking out of the house. It is going to have a relationship on the refresh rate. Probably not on your oxygenation level, probably not on your cost either. So, but it will have an impact on the percent of your home serviced. So these are all of our relationships between our form and our measures of quality. Now ideally what you would have is your form is a circle dot where there's only one circle dot in the entire row and in the whole column. When the more relationships you have, the dirtier this becomes, because it means if I want to increase the speed of heat removal, I now have to look at these 4 elements simultaneously. If I want to look at percent of home serviced, I need to look at the vents, I need to look at the intake. If I need to look at the oxygenation level, well here now I'm only looking at the internal unit. So that's a nice feature there. Throw this on the flip side. Over here, this is where we rate existing units. So on a scale of 1 to 5, how well do existing units do? Let's say existing units don't really get a bunch of air out. They're pretty moderate in speed of heat removal. Refresh rate is pretty moderate. Percent of home serviced is pretty good. Oxygenation level is pretty bad. Our cost is moderate for the market, and their ease of maintenance. Usually oftentimes what you'll do is you'll have like one baseline system where you'll say, this is this. Sometimes what people will do, and what the book does, is they try to go for, it's a 1 to 5 scale, and you'll just rank them this way, or you may have, some people will just say the existing technology compared to our product, and then they'll either rate this up, down, or equal. So, but there's a couple of different ways to do that. Up here, so that was step 4. Step 4 is kind of your matrix. Step 5 is existing solutions. Make sure I'm following this well enough. I'm trying to teach to the book again. Oh yeah, they didn't do that. Step 4 is actually your form. 5 is your matrix. 6 is your existing solutions. The book switches these two. I like doing it this way. Step 7 is an evaluation here, where what you do is you take these weights, you multiply them by these numbers, and you ultimately add up everything that's in this column. So here this would be a circle. The circle is times, if we're going for the user needs, we would multiply the circle, which is a 3, times 2, and this cell right here would have a value of 6. This is a triangle, which is 1, goes 15. This cell right here would have a value of 15. Okay, and this up here is a 9. 9 times 12, that cell up here has a value of 108. Okay, so we would add up this column, 108, 15, 6, math in my head. Come on, head maths, come on. It should be 139. Okay, so you'd have 139 in this category, which isn't not a very good score. You want to have, you're aiming for low scores here, kind of. But really this row here is going to tell you how important this form is to your overall design. So here, if I look at the internal unit, this is 9 times 2, which is 18. Okay, so we got 18 plus 3 times 45, that's 45. That's 9 times 6, that's 54. Plus 3 times 8 is 24. Plus 1 times 12, plus 9 times 20. So this column here is going to be probably somewhere around 300. This is the most important unit for this design. Breaking this down and looking at redesigning this, actually maybe separating it into different systems, that might be a good idea for as we evaluate and optimize this system. We reduce this number a little bit. So it's only got the 9 and the 20 instead of having all of these other relationships. So we would do that for each category, and we would get ultimately just a score down here. Okay. The last step of the House of Quality, as your book frames it, is this top part here, which is the roof. What we do here is I'm going to go ahead and draw some diagonal lines. Wow, we should have drawn this a little better. We've got one cell here. Oh, how do I draw this? I'm trying to make sure I draw this right. Yep. Each one of these gets a little bitty triangle that goes on top of them. Oop. And this one goes here. Yeah, kind of I should have just redrawn the triangle. Let me try that. This is not an art class. I struggle with the most basic of straight lines. There we go. Already better. So each line has one that goes up at a 45 degree that way, one that goes up at a 45 degree this way. You have 90 degrees between them, so it forms squares. And then what you do here is we've evaluated these relationships. Now we need to evaluate what the relationships are between these. We're going to go ahead and draw an X if these depend on each other at all. So here, the outside coils, do they depend on the amount of power that's provided? Well, the outside coils, quite frankly, do. So there is a relationship that exists here. The internal unit heavily depends on the power. So if we go, the intersection between those items is going to get an X. The internal unit doesn't really have any connection with the outside coils or with, I mean, it has a relationship with connections, but those can be designed completely independently. The internal unit is going to, well, it doesn't really have an impact on the vents or the intake. Vents and intake have a relationship with each other, but they aren't really dependent on power, connections, or the outside coils. So yeah, we don't have a ton of relationships between our components, which means this is already a pretty good system. We could break apart this internal unit and look at the different relationships there. It should get power, yeah, power's there. So, but this is our house of quality. What we're gonna find is this is the most important component. Any changes we make to this component are going to impact most of the design. And if we're looking at upgraded models, you just increase the internal unit, you're good. Here, this is a very important component too. The ones that have the highest rating, so here the 12 and the 20 and the 15, anything that has a relationship here in your rows that have the high weights, those are going to be the most impactful components. Okay. And certainly that's going to show up in your scores. So that's house of quality. Again, I'm going to post another video of somebody doing this for a different one. You will have to do this for project 2. So tune in a second and we're going to be covering